All right, go ahead, Shreya. Thank you so much.
Thank you for having me. Thank you so much for all of you joining me here. And today we are going to talk about big O notation. So firstly, before we start, I would like to ask a small question to all of you. Have you ever been in a situation where you were provided with a question to write a code, and once you're done with writing the code, the interviewer asks you to tell him about the complexity of the program? Have you ever been in that situation?
Yes.
Yes. Yes. Yeah, I know most of us have been, but I just wanted to hear from you all. Not yet, but I'm getting it. You should, but definitely not after this session. I hope so. All right. So, why do we get so scared when we are asked about the computational analysis of our program? Maybe because we don't know how to calculate it, or maybe we are scared of the next question that can come up from the interviewer to try to optimize our code and try to make it more efficient, and which we know we might fail, and hence we are a little bit scared of going into this big of complexity and diving into this computational analysis. But today we will be covering the big O notation, not only why you will use it, but also how to calculate it. So please bear with me as I start and go forward. Thank you so much for having me. Hi, this is Shreya. And Monica, can we go forward to the next slide? All right. So what is big O notation? So big O notation, as defined by Wikipedia, is a mathematical notation that describes the limiting behavior of a function when the argument tends towards particular value or infinity. Now, okay, this is a formal definition, but what does this mean actually? So, as it says, it is a mathematical notation, so a language that is used by mathematicians, computer scientists, or in general the developers to describe and to define the analysis, or we can say the scalability of our program, that how is it going to perform and how efficient our algorithm or the code that we have written is in general. So to know how efficient it is going to be, we need to compute the computational analysis, and when we do so, we get to know how efficient our program is. So that is nothing but just a way of describing the efficiency or the performance analysis of your code or your program. But the question is, how do we know what is going to be the performance or what is going to be the efficiency of our code that we are going to write? So for that purpose, we have two terms. Obviously, we use algebraic terms because it is a mathematical notation. But then there should be some criteria over which we can calculate the efficiency of our algorithm. So what is that criteria? So does anybody want to answer that? No? If anybody is answering, I can't hear it because you are all on mute. Yes, time and space. Correct. That's right. So time and space are the two parameters based on which we calculate the efficiency of our algorithm or our program. So we will be focusing more on time and lesser on space, but we will talk about both definitely. Monica, can we go to the next slide?
Yeah, can you just get maybe a little closer to your microphone?
Oops, am I not audible properly?
It's like when you back, I think as you're standing, when you back up a little bit, it gets a bit hard to hear.
Thanks for letting me know.
Yeah.
All right. So since that was a little bit theoretical definition, so I have also included one mathematical definition of our big O notation, so we can understand what does it mean by the terminology big O notation in terms of mathematics. So in terms of mathematics, as defined by University of Washington, big O is all about finding an asymptotic upper bound. Now, these are heavy words, asymptotic upper bound, but what does this really mean? So upper bound is the worst case, or we can say the maximum number of computations that can be that we can expect to perform, or that can be expected by a code to get performed to achieve a desired output. Let's say you are here, you are having a problem to solve, and you're writing a code. So that code will require to make some computations, right? For example, let's say you have an unsorted array and you want to sort it out. So when you are going to sort it out, definitely we are going to make some computations. We are going to write some function that will be doing some calculations, and there will be some number of computations that will be repetitive. So these repetitions of computation, so it takes some time. And because we cannot measure this time that is taken by a code to perform that whole calculation, we cannot measure it in terms of minutes or seconds or hours. And it is something in milliseconds and micro milliseconds. It is so so insignificant that we cannot realize it. But when we are doing a larger chunk of calculations on regular basis, and we are having a larger code in practical scenario, so it creates a wide impact. Why? Because based on one code, if it is going to take more time than expected, then it is going to impact the other code that will be getting executed after that. And so in a larger chunk of data, when we see a lot of code written over in some, in industry or in projects, in practical scenario, it creates a lot of impact that we cannot realize while writing code. But that's why this bigger notation comes into picture, and we need to be very mindful of the efficiency of our algorithm or the code that we are writing in. So again, coming back to my point where I said that because we cannot measure it in terms of minutes or seconds or hours, so what is the criteria or the parameter in which we can measure it? So that becomes number of computation, because it is easy, it is visible, and it can be calculated, because we can see when we are writing program, we can see how many number of iterations we are performing or how many number of computations are we doing. So based on number of computations, we get to know what is the time complexity of our program. And that's why we focus on the number of computations instead of minutes and hours or seconds, because that is something that we cannot really calculate, and we don't get much information from there. But with the number of computations, we can definitely tell, oh, if it is 10, let's say for a smaller code, if it is going to take 10 iterations to get a desired output, so definitely computer will be performing those 10 calculations, okay? Internally, obviously, we don't see it, but yeah, internally it takes time to perform those iterations. So talking in the terms of mathematics, uh, like I have written here, Fn is equals to order of Gn if there exists positive constants C n naught such that function of n is less than or equal to C of G of n for all n is for all n greater than or equal to n naught. Now, what does it mean? First of all, when I say the capital N presents the set of integers, or we can see it as a number of elements that are going as an input set. So I hope I'm clear here. If not, you can let me know in the chat, and I will try to take your questions and I'll try to answer those, because maybe these things can get missed because these are small things, so these can get missed in the last during our Q&A session. So if there are some small questions, you can ask me in the chat, and Monica will also be helping me answering those questions. Okay, coming back to this function of n. So the capital N here, this represents the set of integers. Now, what do we mean by set of integers? Sorry, not set of integers, but the set of natural numbers. I'm so sorry. Set of natural numbers. Natural numbers are represented by small letter n in mathematics, and the capital letter N specifies the set of n natural numbers. So when we say function of capital N, so we are saying that they are going to be an array or a list, or we don't know how many input is going to be there, input elements are going to be there. So that's why we have written n, that is set of n natural numbers. That because when we are doing computations, we are calculating it for all those elements present in the array. So that's why it becomes a function of capital N instead of a function of small n. Okay. Now coming back to the right side of the equation, order of G of n. What does this mean? So let's keep order of aside, because definitely we are calculating big O. That's why we are talking about order of. So I'll come back. I'll come to it. I'll come back to it. But before that, I want to define G of n. So what does G of n mean? So G of n is the order of the graph when we say the order of the G for n function. So here the G of n is nothing but our big O that we are calculating here. So G of n means what is the rate of the growth of our function as it tends to a particular value, or it could be infinity, it could be zero, it could be something, anything, which is here the upper bound that we are talking about. So what does upper bound mean? Upper bound is the last limit in the worst scenario till where your program can go in terms of its performance. So let's say if a particular program where we need to let's say we need to do some sorting or some searching, okay, and we don't know what input data set we have, okay. So based on the way input data set is arranged, that is going to be the deciding factor for us. How many computations are we going to do, or how many computations are going to be performed? Why so? Because let's suppose you are given an unordered set of array, okay, and you need to arrange it in an ascending order. But you see that all the elements are completely in a different place from where it should be. Okay, it's like you have to swap all the values, each and every element to get it in the right order. Or there could be another array where only one element is slightly off bit and other elements are already at the desired place. So in that case, what will happen to sort the second array? Definitely, it will take less time than the first one, because in the first one you're going to compare all the values and you will be swapping all the values. But in the second one, we know that only one element is off it. So it will be skipping all those computations for that swapping. Definitely, it will be comparing, because without comparison, we won't know if it is going to get the sorted array or not. But the time it will take in the swapping, that will get reduced, because we are not swapping, because only one element needs to get reduced. So obviously, for the second array, it is going to take lesser time than the first one. So the complexity, the time complexity for the second algorithm will be better. Why? Because the time taken to perform that computation is going to be lesser than the first one. And for the first one, what will happen? Let's suppose there is a burst complexity. Burst complexity means we are going to perform each and every computation that is required to be done to achieve the desired output. So in that case, we are trying to approach to an upper bound. So why I'm explaining this? So you can understand what does upper bound mean. Upper bound is the maximum or the maximum possible time that can be taken by an algorithm to perform the desired to perform the desired calculation and to get the desired result. So that's how we compute it, and that's why we focus only on the rate of growth instead of focusing on the actual program or actual number of computations that we are doing, because we don't know it. It all depends on the input. When you write program, you always use variables. You never take constants, because that is not the ideal way to do that. You don't want that your code to only perform calculation for a particular set of inputs, right? You want it to perform for any input that you provide, and you don't know what input you will get. So based on the input and what number of computations it is taking to get the result, it gets the time efficiency for that particular program. But when we are writing program, we always consider the worst case scenario. Why? Because obviously, if it is going to perform better in the worst case scenario, it will definitely perform better in when the situations will be favorable, right? So that's why we are more focused on the worst case scenario, and that's why we focus more on big O rather than talking about big omega or big theta, because big omega is the best case complexity. That is the best case where you are performing the lesser number of computations that could be possible. And instead of that, in big O, we are performing the maximum number of computations possible to get a desired result. So I hope that was clear. And that is why we use this term order of G of n, because we are only focusing on the rate of growth instead of focusing on the whole computation. If you see the graph for a particular algorithm, we will always notice that the graph, it might be curvy, it might reach somewhere for a particular value or for some time, but as the n grows larger, we will see a pattern. The rate of the growth, it will start approaching a particular value, and the particular value that it is approaching, that is the upper bound, that is our big O. Okay, and as we can see here from the graph itself, if n naught is here, n naught is the first element of the array from where we are starting. Okay, the initial or the small value from where we are starting our computation. Like when we use for loop, it could be I is equals to 0. So let's treat n naught as I equals to 0 for the first element or the first computation that we're doing. Okay. Now if you see the C of G of n, which is what? Which is our order of the order of complexity. Okay. Okay. So for the second graph that we see, now the C of G of n, if you see it is approaching a particular value, but our function of n, it is curvy. It is not, it is not the same as we have C of G of n. Why so? Because so there is there's one more example that I would like to talk about here. So there are situations where when you are performing computation, you notice that the complexity, when you calculate the complexity, so you get because we are getting a function of n, right? So it could be n squared plus n plus n cube, or n cube plus n squared plus n, right? Anything. But so it could be confusing if I talk it like that. So let's take an example. So let's say we are given an unsorted array, like I talked about earlier, and we want to get it sorted. Okay. So to sort that array, we will need to take two for loops. Why so? Because the first for loop will be used to iterate through all the elements of the array, and the second loop that we will be taking, that will be used to swap the values and to compare the values from the next element and going forward, going further down the line to all the elements in the array. So in that case, what will happen? Suppose you start from the first loop. Okay. So in the first loop, let's say there are 10 values, and these are all unsorted. So when you will start from the first element in the array, so you need to compare it to all the other elements of the array. Okay. So when you're doing the computation, we are not just comparing it with the second element, but also the third and fourth and fifth, and going on till the last element of the array. So, but here is the catch. For the second loop, we are starting with the second element, not the first one, because the first element you have already taken in the first loop, right? And here you will be starting from the second element. So the number of computations required to do this comparison will get reduced to n minus 1. Am I clear on this? Because see, first and foremost, we are taking all the elements, right? In the first for loop, we are taking all the elements of the array, because we need to check for every element if they are at the desired place or not. But to do so, we need to compare it from the next element. So because we're starting from the next element in the second loop, that's why the number of computations will become n minus 1. But for the first loop, we will be doing n number of computations, because we need to check for every element from the first loop. So what will happen? From the first loop, you will take first element, and then you will compare it to all the other elements of the array in the second loop. And wherever you will see that it is not a smaller value, you will swap it. And doing so, you will get the number that you took, the first element of the array, at the desired place, because you have already compared it. By then, you have already compared it to all the elements. So by getting it swap, you will get it at the right value was 12. So when you compare it to the first value 10 to 12, so you will see that it needs to be swapped, right? Okay, sorry. I'm sorry, I confused it. The first value should be 12 and the second value should be 10. Okay. So then 10 will be lesser than 12. And then when you swap it, so the 10 will come here at the first place and 12 will go to the next index. Okay. But what if the third element is 8 or 7 or 9? It could be anything, right? So now we are comparing that 10 to every other element, right? Sorry, not 10, 12, because we started from 12, right? So we will be comparing 12 to each other element, 7, 8, and 9. And likewise, what will happen? 12 will end up at the last or maybe at the middle, wherever it fits better, right? But the other element of the array will not be sorted. So again, what will happen? Now we'll take the second element from the first from the unsorted array, and from there, when you will take that value, it will be 10 because it was in the unsorted array, you are taking it in the raw form as it was provided in the input. So that will be 10, right? So you again need to compare it to all the values, right? So doing so, you will notice that you are performing totally n into n minus 1 number of computations because you have to check it for every element and you need to go till the end, right? Because without comparing, we don't know what comes from the array or what is the next element in the array. And that's why we need to compare for each and every value. We may not need to swap every element, but definitely we will check for every element. Okay. So let's say we are performing all the computations in this case, and we need to perform all the calculations that are there. So in that case, what will happen? We will be doing n into n minus 1 number of computations, which boils down to n square minus n. Now, n square minus n, if you look at it, so for a bigger, very bigger value of n, minus n becomes very negligible. And again, in this case, it is minus n, but it could be plus n as well for some other program. It could be n square plus n. Definitely, when we are subtracting something, it is only going to get lesser than n square. It will never be greater than n square. But even if we are adding it, okay, let's say in some other program we are adding it, and the number of computations taken are n square plus 1 plus n. So in that case also the n will become negligible because for a very bigger number, after all, it is just a constant, right? It is not going to change its value. So when we are approaching towards infinity, it becomes negligible. And that's why we say here, for some constant c, we are only focused on g of n. So that g of n here is the rate of growth that we are focused on. The dominant term that we call in technical language, that is n square. And we will be dropping the constant, that is minus n or plus n or whatever is there, we will be dropping that. And that's why it becomes g of n rather than f of n, because f of n actually was n square plus n. But here we are only focused on g of n, that is n square, and we are dropping the constants and the coefficients, okay, which we also call non-dominant terms in technical language. So how do we read it? F of n belongs to order of g of n. So that's why we write it as order of g of n instead of writing directly g of, because f of n cannot be equal to g of n, right? Because we are dropping the constants there. But it is of the order of g of n, that is n square, which means we are only focused on the rate of growth, how it is approaching to a particular value rather than the actual number of computations that we are doing. Okay, I hope I tried to explain it in detail and it was clear. A few points to remember here are we are concerned, like I said, with how f grows when n is large rather than being concerned on any small n or constant factors, because it becomes negligible. Again, it doesn't matter when we are talking about such larger value. So that those smaller values or those constant factors doesn't matter so much. It becomes insignificant. And Fn can grows no faster than Gn. So why it is so? Because as I said, we are only focused on the rate of growth, right? So what will happen, because Fn is the actual number of computations that is required, but in G of n we are only focused on the rate of growth rather than the actual number of computations. So in that case, obviously, Fn will always be having more value than Gn, right? Because in Gn, we are dropping the constants and we are dropping the non-dominant terms. So it can never grow faster than Gn. Our Gn will always approach the upper bound and it will always grow faster if we compare it to F of n. Since it is the basic, I want to spend some more time on this, but I would like to ask if there is any questions from you that I can answer at this moment. Fn will have more values than G of n, is that right? Yes, because in G of n, we are dropping the constants. So it is not like having more values. Don't focus on number of value, more values or lesser value. When we talk about f of n, we are not talking about the set of input data. We are talking about the function of n. So function of n will always yield us the number of computation. So there is not more value. There is just one value, that is the number of. It is basically the number of computations that it is doing to achieve the desired result. So that's why when we are dropping the constant and coefficient, it is reduced to Gn, where we are only focused on the rate of growth of our graph, where it tends or it approaches to a particular value. Any other questions? All right, I'm glad I could answer that. Any more questions from anybody else? All right. Monica, we can move to the next slide. So now we'll talk more about time complexity. As I mentioned, it is measured in terms of time and space, but we focus more on time because obviously time is precious and space is cheap compared to time. So we will be focusing more on time complexity rather than space complexity. So first and foremost, we have is constant time complexity. And by the definition of Wikipedia, an algorithm is said to be a constant time algorithm, also written as order of 1, if the value of t of n is bounded by a value that does not depend on the size of the input. Now, what does that mean? It means that our number of computations that we are doing in this case, that remains constant. It could be anything, but it is not changing based on our variables or based on the size of our input. It could be anything like, for example, you can take any number of elements in an array and you can try to find a particular value. Okay. So when you know the particular value, like in this case, if you see at the graph, I have taken the example of y is equals to 50. So here, y remains constant. It is 250. It is not dependent on any variable. We don't know whether. So let's say we have x is equals to 1, 2, 3, whatever value we have. Okay, our y is going to remain constant. We are not changing our y based on some other variable x. So in this case, what will happen if you are given an array where there are, let's say, n number of data, okay? And in that case, let's say there is an array of 50 numbers, okay? And in that 50 numbers, there is also a number which is 250. And you need to find out that 250 from that array of 15 numbers. Now, what will happen in this case? Even if it is 50 number of elements or 100 number of elements, you only need to find 250. You know already what single element are you looking for. There's a specific element that you are concentrating on. So in that case, the number of computations that are required will always remain constant. One very good example of it is our select query in database. So whenever we start select query, so why I'm taking the example of select query, because since this is the very first time complexity, so let's not dive in the programming language of Java and Python. Even if you don't know how to code, but you always know how the database works, right? SQL query is always the simplest one. So the select query that we use for our database, it is the best example of constant time complexity if you know what you're looking for in the records. let's say I'm looking for my record. Let's say there is a customer table and I'm looking for my record. So I know my first and last name is Shreya and Agrawal. So what I can write, simply select all from customer where first name is equals to Shreya and last name is equals to Agrawal. So it will always fetch me only my record, right? Nothing else. And it will take constant time complexity. So whenever we are accessing any single element, any specific element in an array, it is always going to perform only one operation, and that's why it becomes the constant time complexity. And another example of it is finding the median value in a sorted array of numbers where you already know the number of elements present in that array. So you only need to find that median value because you can calculate it, right? You know what the median value is. So you can obviously just write down that there will be a simple query where you will be saying if this particular or if let's say you will take a for loop, okay, and in that for loop you will write for I is equals to 0, I condition will be I less than n or less than or equal to n I plus plus. So in that case you will be only looking for that if a of I is equal to particular value or not. That is the whole code that you will write, nothing else, nothing more. So yeah, if it is, it will fetch that. If not, it will just skip it. So it will remain always constant. Was it clear? You can write in chat. Any questions? So like variable assignment and returns would be constant. Sorry, I didn't get your question. Can you please elaborate? Are you sure? Okay. So let me explain again in simpler terms. So here what is happening that it is not dependent on variable basically or the number of elements that we are providing. It will always remain constant. The number of computations that we are doing in this case, uh, maybe instead of helping my SQL query might have confused people, but I just want to say that in this case, the number of computations that we are doing that will remain constant. Okay, it will not depend on how much size of the input set is. Okay, so that is where it becomes a constant time complexity in simple terms. All right, let's move to the next slide then. Linear time complexity. So the next one here is linear time complexity, where we see that the number of computations that we are doing to achieve the the desired outcome is directly proportional to the size of the input data. Okay, so if you see the graph, it is the the straight line. Why there's a straight line? Because it is connecting the two dots, and which simply means that if you see if x is equals to 2, then y is also equal to 2. Or it could be some proportionate value. It could be if x is equals to 2, then y is equals to 4. Or when x is equals to 4, then y is equals to 8, like that. So it is going to be in proportion of what the size of the input data is. So, and here I forgot to mention in the graph, what I should have. So here the x-axis represents the number of elements that we are taking in any computation, and the y-axis represents the time it is taking to do all those computations. Okay, and going forward, we will have to keep that in mind that x represents the number of elements and y represents the time it is taking to compute those calculations. So a very good example of this is printing all the elements of an array. So let's say you have an array with n number of elements, okay, and you need to print each value from the array on the console. So while printing that value, you will be going through each and every value, right? So in this case, what is happening? You'll see every element is taking equal number of time, right? So that's why we say that it is growing in direct proportion to the size of the input data. So if it is like if there are n elements, you will have to print it. You will have to print all n elements, and when you're printing those n elements, you will be iterating each and every time for each and every element, and it's like reading, accessing those elements, and then printing it. Again, accessing the next element and then printing it. So that's why it is in proportion to the size of the input data. Another good example is when you are given an unordered array and you need to find the minimal value. So in this case, you don't know. So that is the basic difference between the constant time complexity and linear time complexity. In this case, you don't know what the minimal value is. In that case, you were aware of the value already. So you knew what to look for. But here you don't know what to look for. It is an unsorted array and there is some minimal value. It could be anything because you don't know what is coming from the array. So you will have to look for each and every value. But because you only need to find the minimal value, you won't be doing swapping or something. Whenever you find it, you can just print it out. Okay, so there are no other computations required. That's why it is in proportion to the number of elements that we have in the array, and only comparison is required, but no swapping and sorting and other things are required here. And that's why it is the best example of linear time complexity. Any questions? No, maybe. All right, I take it as no. Then let's move to the next slide. Logarithmic time complexity. What is logarithmic time complexity? As the name suggests, here the number of computations that we are doing, it is going to be log of n. And here the log of n could be, so what happens when n is some number of elements, okay? So by logarithmic time complexity is having this kind of graph. If you see the graph goes like this. So what does this mean? It means that as n, as we are approaching towards n, okay, it means that when as we are taking more and more elements in an array, or we are trying to do more and more computations. So sorry, not more and more computations, but as we are trying to take more and more elements in the array, so at that time, what will happen? The computation will start to getting reduced with the growing value of with the growing number of n. The number of computations that we will be doing will start to get reduced. It is not so. It is completely opposite of what we saw earlier. We saw that it is in direct proportion, right? In the case of linear complexity, it was growing directly in the proportion of the number of elements we are taking. But in this case, what will happen, regardless of the base of the algorithm, it doesn't matter here. But as we will start to take more and more elements, the number of computations required will be lesser. So I may not be clear as I mentioned this theoretically, but when I will take an example, it will be more clear. So binary search and binary tree are very good example of this. So what happens in this case? I'm not sure if anybody has a chance to go through it, but in the case of binary tree, what we do, if we are given n number of elements, okay, so we just divide it from between. We don't take all the number of elements, but we divide n by 2, and we focus only on n by 2, okay. So when we are focused only on n by 2, so in the n by 2 elements, we will take that particular value that we are looking for, okay, and then we keep on reducing it by n by 2, n by 2, n by 2. So what is happening here? Suppose you are given an array of 10 elements, okay. So firstly, you will divide it in the middle, okay, and you will take 5 elements here, 5 elements here. Now you will again break it down, and you will take the middle point, the median, okay. So that will be the third element, and you will see, you will compare it from both left side and then the right side. So likewise, when you start doing this, you will see that you are not required to perform all the operations because you are only comparing it with one value or two value, which is adjacent to it. Okay. So when you're doing that, when you're comparing it to the adjacent value, so you will see that doing so, it will already get sorted by the time you could reach till the end. And that's why the complexity gets reduced to log n. We'll talk more about this as we will as we'll go forward with our next session. And that's why I'm not covering much in detail. I'm just talking about the basics because as I can see in the chat that it is the hardest one for me to understand. So that's why I'm just giving a brief introduction so you can understand that what is the concept and what is the basic idea behind any algorithm and how to approach it. Because when you know how to approach it, what is the concept behind it, then the calculation and writing the code is just a secondary and byproduct. Okay, so firstly you need to understand the concept, what is actually happening. So I will suggest everyone, if you are new and beginner to learning algorithm, so before trying to jump to write code, it is always better to try to to solve your problems on paper or trying to solve it, by by doing computational analysis and step-by-step approaches like we see in books. Okay, so it will help you understand every step of the computation, what is actually happening there. I didn't want to make it more complex. That's why I've not included the slides, but we will definitely cover it in our next sessions when we'll go further and we'll discuss every algorithm in detail. Giving it more time. But the basic idea here is that we are reducing the number of elements. We are keeping it half, 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 half. So when you start to do it half and half and half, you will notice that in each step, the number of computations that you're doing is getting reduced. And when it is getting reduced, so for a larger number of elements, when you will, the step goes like this. So when you are reducing it, the number of computations that you're doing, it becomes very, insignificant in terms of how many elements are present there. And that is why it is log n. I'm not sure if it is clear, but yeah. So a very good example is when we have 8 elements, suppose. Okay, so in 8 elements, to sort that 8 elements or to find a particular value, it will only take 3 computations. Because what will happen in the 8 elements, like I said, you will divide it from the between, okay, and you will get 4 elements here, 4 elements here. Then you will again divide it and you will get 2 elements, 2 elements, 2 elements, and 2 elements. So there will be four, let's say there will be 4 small blocks of 2 elements. And in each 2 elements, you are only comparing one with the other, and here again one with the other. So like that, you are doing just 4 comparisons. And with these 4 comparisons, you're already sorting them, okay? And now what you need to do, now you have to combine them. So these 4 separately are already sorted, okay? Let's take it as a pair, okay? So that 4 pairs are already sorted in in uh, in their own, let's say they are in their own shells, okay? And here they are sorted. Let's say the first one was 4 and 8. So we have already sorted it 4, 8. And here we have 12 and 10. So we have already sorted it 10 and 12. So like that, we are getting 4 pairs which are already sorted. Now what we need to do in the next step, we need to combine those two. Now when we will combine these two sets, so what will happen? You will only be doing the computations between which one is having the more value. If let's say, like I said, one is having 4 and 8, and then this one is having 10 and 12. So when you combine, you will only have to swap only 1 or 2 value maximum. Okay, and likewise, it will happen for this next one also. So now you're again combining the right side of 2 blocks, and when you combine that, you only do one computation here. And likewise, so now you have got 4 elements in here and then 4 elements here. Now we only need to combine them. Again, you will be doing just 1 or 3 starting because they're already in ascending order here and ascending order here. So if you see, there are 8 number of elements, but you did only 3 number of steps and you got the result. I'm not sure if I was able to explain, but let me know if you have any questions. So yes, I would like to take this question that does log n means log base of 10? Base could be anything. Base does not really matter here actually, because again, base is any constant value that is not changing. So we will not focus on base here. It could be any constant value, but as I've written here, since log n to the base a and log n to the base b are related by a constant multiplier, and such a multiplier is irrelevant to Bibo classification. Again, the same thing, because when we are talking about a larger set of input data, so at that time, these constant multipliers at any constant value becomes very insignificant and irrelevant. So we won't be focusing on that because we only have to focus on the rate of the growth rather than the growth itself. I hope I was able to answer. And there is very nice graph shared by Monica that you should go through. So it will help you understand how does binary search and sequence work. Any questions before we move on to the next slide? All right. So let's look at the next slide where we are going to discuss log linear time complexity. So log linear time complexity is by definition of Wikipedia, it is by the way also called quasi-linear time, and it is nothing but just where the number of computations that you're doing for performing any function is n log uh, log to the power k of n, where k is again some constant, so we can ignore it or we can consider it, doesn't really matter. It could be any positive constant, any value that will become insignificant in a larger picture. So in this case, what happens? Uh, n log n is the running time when we are performing any operations n times. Okay, so it is also denoted as theta of log n. So actually, I would like to talk about the example directly here. The good example for this is merge sort and quick sort. So have you ever gone through quick sort algorithm on Wikipedia? No, because there is a very good GIF that represents, I forgot the name, but yeah, Tower of Hanoi, right? So the Tower of Hanoi is a very good example of quick sort. So what happens in quick sort? I know it is a little bit complex, so I won't go much in detail. I don't want to confuse you, but what happens in merge sort? Let's talk about merge sort. So in merge sort is saying that like is the name of like symbol before login in the first place. That is theta. That is not O. That is theta. So theta is the symbol that we use to represent the average time complexity. I'll talk more about average time complexity as we go further, but for now it is just the representation of average time complexity. So n log n, as we can see from the graph, n log n is nothing but n multiplied by log n. So for merge sort, I'm not able to actually. Okay, so has anyone? Yeah, this is the tableau. Thank you, Monica, for sharing this. So, what happens in merge sort when we are having, let's say, we have to sort an unsorted array. Okay, so in a sorted array, sorry, in an unsorted array, when we are going to merge, when we are sorting, we are taking a particular value as uh, as a reference point. Basically, it is a pivot, nothing but the pivot value. So it could be a median value or the middle value that we consider as a pivot, and we try to compare other values with that value. So, like I told you in the previous example, that we were breaking it down to half number of elements, right? So here, what we do, we take a pivot. Let's say we have n number of elements. Let's take the example of 8 elements. Okay, so we have the 8 number of elements. So we will take a median value. Okay, it could be 4 or 5, or let's say to take it easy, let's take an example of 9 number of elements. So we will have fifth element as the pivot. Okay, because it is in the middle. So what we will do, we will treat it as a reference point. Okay. Now what the idea is that we need to get all the elements lesser than that pivot element in the left side and all the elements greater than that pivot element in the right side. So what will happen in this case, that all the elements of the left side will already get sorted, and from here from the right side again you will get all the elements that are greater than that. I'm not sure if I'm able to explain that, but the basic idea is that you need to grab a reference point, and that is why we call it pivot. So basically, you are not comparing all the values to each other, but only to one value, that is the pivot value. So you need to compare. That is why it is the quickest. That is why it is also called quick sort and merge sort, because it is very quick to do. You don't need to compare all the elements to each other. You are just comparing it to one element. Any questions on this? I'm not sure if I'm able to explain this. Yes. No? Okay. So moving on to next slide, we have quadratic time complexity. So for quadratic time complexity, as the name suggests, it is the n to the power n to the power 2, which is also called n square or n squared. So here what happens that the number of computations that we are doing is exponentially growing. So I will also sorry, not exponentially growing. I'm so sorry about that. It is growing in the terms of polynomial. Sorry, we treat it as a polynomial. So we also call this quadratic time complexity as a subgroup of polynomial time complexity, you can say, because what happens in polynomial time complexity, we consider that the 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 power that we see here, that is 2, it is some polynomial function. So why polynomial function? Because it could be n cube, it could be n to the power 4, and that's why we consider quadratic time complexity as one of the polynomial time complexity. So why I'm talking about this, because I've not included n cube, but n cube is also polynomial time complexity, which is also called cubic time complexity. But these are all, it is like polynomial time complexity is like an umbrella under which quadratic and cubic time complexity, all of these fall in. Okay, based on what are the number of computations and what is the order that we are getting. So if it is n square, it will become quadratic, and if it is n cube, it will become cubic. But in a bigger picture, they are all polynomial time complexity. Okay, so again, when we talk specifically about quadratic time complexity, in this, the performance of the algorithm will be directly proportional to the square size of the number of input data you are taking in your program. Okay. Yes, nested loop, very good example. Nested loop is a very good example of quadratic time complexity, like I talked about earlier, where we were comparing all the elements to each other till we go till the last element, and then we get n square. So I think we have already covered that, and I have written in the example in the bullet point that to sort an array of size n in ascending order, we need to use the insertion sort algorithm, which is O of order of n square time complexity in the worst case. Again, that is the worst case when we are assuming that we need to perform all the computations that are required to get the output. maybe we don't need to perform all computation because array is already 90% sorted, and you just need to perform 2 or 3 operations. So that will be the best case, obviously, but we will focus always on worst case complexity. And whenever we are doing all the number of computations, then it will become n square in this case. So any questions? Because we have already talked about this in earlier in our previous slides, that's why I'm not giving much time on this one. But if you have any questions, I will be happy to take that. No? All right. Monica, can we move on to the next slide? Okay, the last one in the list, exponential time complexity, by far the worst one. So the exponential time complexity, in this case, what happens whenever we have n number of elements in a program or in a function to perform computations. So the number of computations get exponentially doubled, with each addition to the input data set, the number of computations that we're going to do gets doubled, or it grows exponentially, basically. Very good example of this is Fibonacci series. So if anybody knows how we calculate the Fibonacci series and how we calculate the sum of the Fibonacci series, so you will see that Fibonacci series keep on increasing, right? It keeps on adding the last 2 elements. So it is like 1, let me write in the chat. It is 1, 1, 3, sorry, 2, then 3, then 5. So what is happening here? We are basically going further in the series. So we are adding the previous 2 elements, and then that's how we get the next element. Okay. Now, if you have to compute these values, so you will keep on getting you will keep on computing, right? So if you see here, it is increasing exponentially. 1 plus 1, 1 plus 2. So it needs to add more and more numbers now, and it will keep on increasing till it reaches infinity. So that's why the graph goes like this, because it grows up and down like in no time. You will see it is started from -2. At -2, y value was here, okay, very close to x-axis. But as it reaches till 4, it is growing like this. So from -2 to 4, we can see how far it has gone. It has already reached 16. So likewise, it keeps on increasing, and the growth is exponential. So that's why it takes much and much time to compute these algorithms, and it is not considered a best practice. When we are writing code, we should never use exponential time complexity. Any questions on this one? All right. So now we will discuss about best, average, and worst time complexities, like I mentioned during the in the beginning. So the best time complexity, as I mentioned, it is the case where our algorithm will perform its best in the most optimal conditions, under the best or you can say the most favorable situations, like I mentioned, where you will be given an input where you need where you need not do all the computations for sorting the array. You are already having n minus 2 numbers sorted, and you just need to sort the 2 numbers. So it will take lesser time, and that's why it becomes the best time complexity. So in this case, for example, I've written the simple linear search on a list occurs and the desired element is the first element of the list. So what will happen? You already know what you're going in linear search. You already know what elements you're looking for, right? So, and we have in the linear search, like we saw in the beginning, we are moving to each and every element and looking for a particular value, because the value is not changing. So let's say we are looking in array and looking for the value 25. So when we are looking for 25, maybe 25 is the first element in the array. So you need not check all the elements. You already got 25. So that was the best case, because you are not doing all the computation, but you got it at first. For average time complexity, as the name suggests, it is average time. that could be taken by an algorithm to perform those computations. Means in any typical situation, how many computations will be required or how much time will it take to get the desired result, that will be considered as average time complexity. And it is mostly based on, it is not based on worst case or best case, obviously, but an average case where some elements could be juggled up, some elements could be at play. So you need to perform all the computations, but it is not like you're going to get the answer in just one or two computations, but you will take a while. So that's why it is considered average time or typical time complexity. And yeah, for the representation, like I got one question earlier. So I have not mentioned here, but for best time complexities, we use omega, the symbol of omega, to represent the best time complexity in computer science language. But yeah, in industry, we just keep it simple. We only use the technical term big O, or the order of algorithm or order of the code. But in the computational science language, the best case complexity is always denoted by omega. The symbol is omega. Instead of O, capital O, we write omega. For average time complexity, we denote it by theta symbol, and for worst time complexity, we denote it by a big O, which is our upper bound, that is a capital O, and the order of worst complexity. So I will not talk much about worst time complexity because we have already been discussing about it. The upper bound, the worst case scenario, where the program will perform in the worst situation where you are performing all the computations for all the inputs of any arbitrary size. So it could be any number of elements, or it could be a set of natural numbers, or anything where you're performing and you're taking, you're using all the resources, all the space and time you have to perform those computations. So in that case, it becomes the worst time complexity. All right. I think we have already covered this time complexity. So next, we will just look at this graph. This is a very beautiful graph which is used everywhere to understand the basic difference in each of these complexities that we discussed. So if you'll see here, there are some you can say a range that we see here in different colors. So what does this range represent? This range represents the possibility of the rate of growth of your algorithm. So if you see the dark green one, that is in the lowest and very closer to the x-axis, that is the order of one. That represents our order of one. So in the worst case, I mean, when we're talking about reaching to infinity, so in the worst case, when the order of one will always remain, closer to x-axis. Why? Because it is constant complexity. So in constant complexity in this case will always remain, grounded. So even if it grows, it will not grow much. As it approaches towards infinity, it will remain grounded to x because the value remains constant. That's why. Next is log n. So log n, as we saw, because as I already mentioned, for the greater number of elements, we are doing lesser number of computations. So as we get more and more input data set, we are doing lesser and lesser computations. So that's why the graph grows like this. So earlier it tries to increase, but it will remain like this. Same is for order of n. So order of n, like I already mentioned, it is always a straight line connecting two dots because it is the constant time complexity. Linear time complexity, not constant one. Linear time complexity. So in this case, it will always be a straight line. That straight line could be like this or this, but it will never go. It will never go elliptical. There will be no curves. It will always remain straight. Because why? Because it will be growing in proportion to the number of elements you are taking for computation. That's why it will always be a straight line. Next we have is n log n. So like we discussed, this whole range, yellow range that we orange, sorry. So this range represents the possibility of our n log n, where we can see our graph and we can see the growth of our algorithm, how it approaches a particular value. And then the first one, as you can see, we have one very beautiful representation over here that the one in pink is horrible, the one in orange is considered bad, and the one in yellow is considered fair, and then we have green ones as good and excellent. So for interview purposes, I will always say and advise that you should always focus on green ones, and you should try to avoid, orange and pink ones. But definitely there are programs that cannot be resolved, that cannot be solved using nlog without using nlogging, because there are some larger chunk of data that needs to be, or there are some computations that are required to be done. So in that case, nlogging is the best case. You cannot resolve them in O of n or log n. So that is where nlogging becomes the best one, but definitely it is not considered a good one. We should always try to focus on log n or order of n if we can, solve any problem. We should always focus on those areas. And yeah, as we can see, as we go further, we have exponential, we have pictorial. So in this, you will see that graph is growing like this, which means that your x value is not increasing. The number of elements that you're taking are not increasing that much, but y is growing, insignificantly and significantly. So y is growing significantly, and as you can see, the number of operations we are doing even for the lesser number of elements, it is growing like this. So yeah, that's why it becomes the worst and the horrible experience. All right. Any questions on time complexity before we go further on our space complexity? Because we are also running out of time. No. All right. Let's discuss a bit of space complexity. So space complexity is nothing but just like time complexity. We measure the efficiency of our algorithm in terms of memory or the space we are requiring to solve a particular program, or to compute those functions, to compute those uh, analysis that we are doing, and for all the operations that is doing. So how much memory or space it is acquiring, how many variables are we using, how many array lists we are taking that are not necessarily required. Maybe we can just, there are ways to do work, like ways to write code where you don't need to take extra variables, you don't need to take extra spaces, like you don't need to define some other array to sort something. You can just sort in the given array itself. So based on situation, based on the kind of programming, and based on the kind of questions we are solving, we always have to look for what are the better ways we can, save space and not use unnecessarily more variables and more spaces in the memory. But why we don't focus much on space complexity is because space is always cheap in terms of time, and we can always trade space for time. So that's why, calculating the space complexity is not that easy as it is for time complexity. So we don't focus much on space complexity when we go for interviews, or in general also we don't, because as I said, space is cheap. So that's why we won't be diving too much into it. But yeah, just to know how it works and what is the idea behind it, I wanted to include this in our slide. So we should be aware of, the concept of space complexity, and what does it mean really. I hope I tried to cover everything. Now, that's the end of the slide. Thank you very much for having me. And going further, we will be moving on to our Q&A round. So if you have any questions that you want to answer, let me know.